Hello everyone. Now usually I'll incorporate a number of example problems into my lectures, but for chapter 22, since it is so heavily focused on the derivations of those fields, we don't really get a chance to see some of those expressions in action. And so what I would like to do at this point is just work out a couple of example problems using what we have from this chapter, and then we'll go ahead and we'll call it good for the chapter, and we'll move on to chapter 23 after this. So I'm going to show two different problems. The first one is going to be based on individual charges. And so what we're going to have here, I'll put a number line on the screen here, and we'll go out 1, 2, 3, 4, 5, 6, 7, and we'll place a charge right here at the 3 centimeter mark. We'll call that, well, let's place the other charge. 1, 2, 3, 4, 5. We'll place another charge right here at -1. And so we'll go ahead and call those charge 1 and charge 2 respectively. And then we'll give them some values. So charge 1, we'll let that be a -50 microcoulombs, and charge 2 can be a +20. Now there are plenty of things that we can ask about this kind of system. We could go back to chapter 21 and ask what kind of force there's going to be, if it's attractive, repulsive. But this is chapter 22, so we're more focused on the fields. And so I would like to know, is there a point somewhere on this number line where the net field in the system is equal to 0? So for that to happen, we will need the combination of field 1 and field 2 to equal 0. And at this point, we might be thinking to ourselves, well, that shouldn't be too difficult, because we have our electric field expression that says that electric field can be calculated as our K value times the magnitude of the charge divided by the distance squared. So wherever it is that we are trying to measure the electric field, that's the value of R. But therein lies the issue. We don't know what that position is out in space. One thing that we are going to have to be a little careful of is that this expression that we've been using uses the magnitude of the electric field. And we have to keep in mind these electric fields are vectors, so they do have directions that they point in, and that's actually going to be critical in helping us to figure out where on this number line we can actually get the fields to add up to 0. So with that in mind, I want to just draw what the field lines are going to look like for each of these charges as they sit on this one-dimensional reference frame. We essentially just have an x-axis here. So for Q1, since Q1 is a negative charge, we are going to see field lines pointing towards charge 1 from either direction. And because Q2 is a positive charge, we will see field lines pointing away from it on either side or either direction. And so right away, this kind of shows us that if we try to consider any point in between these two charges, well, look at what those electric field lines are doing. They're both pointing in the same direction. And so if we combine them, we're just going to make a stronger field. And so there is no way that we can actually combine the electric fields of these two charges at any point in between them to accomplish this. And so I'm not going to consider any points in between the charges, which leaves us with points that are either to the left of charge 1 or to the right of charge 2. Well, if I continue with the field lines that I've drawn here, let's backtrack a little bit and we'll remove these pictures right here. I've lost my origin. There we go. So let's consider a test point somewhere to the left of charge 1. And let's see what color I want to use for that. Well, we'll just use the green. So let's say I'm somewhere over here. Now obviously we can count over, that would be -4, but we're just somewhere to the left of charge 1. So being over there, I would have an electric field line being produced by charge 1 that has to point towards charge 1. That's the way those negative charges work. Field lines point towards the negative charge. But at the same time, there would be, and we'll go ahead and label that. But at the same time, remember, charge 2 is producing fields that point away from charge 2. So when field 2 actually gets over here, it's oriented still to the left. Oops, I wanted to erase that. There we go. And so this combination right here says that we have electric fields that are pointing in opposite directions. So they will be opposing each other. And so that could work. If I were to add those two fields together, the fact that they're opposing one another, technically electric field 2 would have a negative sign associated with it when I add them together, but that is a possibility of adding these two fields together and getting a 0. So something to the left of charge 1 could work. But what about something to the right of charge 2? Could we get something over there to work? And so now we're kind of faced with the possibility that there could be more than one point in this system where the electric field could add up to 0. So let's see what happens if we have a point somewhere to the right of charge 2. And I'll just pick this random point right here. Field from charge 1 has to point towards charge 1 because charge 1 is a negative charge. So we will see field 1 pointing towards charge 1. And field 2 has to point away from charge 2 because charge 2 is positive. So we will see field 2 point away from charge 2. And so that looks like it could also produce a combination that would make 0. So does that mean that we have to set up an expression to solve for both? Well, if we think about this a little bit more, we can actually throw out one of these possibilities, because one of these is actually not going to be a viable solution. And the one that I'm talking about is actually the one over here on this side. The reason for that is if we take our expression for electric field and we actually start plugging some values in here. So electric field 1 is going to be K times the magnitude of charge 1 divided by the distance that charge 1 is from the point where we want to measure. And then E2 is equal to K times Q2 magnitude over R2 squared, but R2 is quite a bit larger than R1. Now again, note that I'm using magnitudes down here for the charges, but I still have to account for the fact that E2 is pointing in the negative direction, so when I add these together I get that negative sign. We want all of this to go to 0. Okay, so now let's see what we have here. I have this first fraction. Actually, since everything is equal to 0, we can factor out those K values. We don't need K in the expression. But for this first ratio, I have the magnitude of Q1, which is the larger of the charge magnitudes. So I have a large charge value, and I'm dividing that by a relatively small R1 value. If we look back up at the diagram, R1 here is pretty small, at least in comparison to R2. And not only that, but we're squaring it. So what happens when you take a large numerator and you divide it by a small denominator? Well, you get something even larger. So this first ratio for charge 1 is actually going to be producing a relatively large electric field magnitude. If we look at Q2, well, Q2 is the smaller of the two charges, and R2 is the larger of the two separation distances. And so what happens if you take a small number and you divide it by a very large number? Well, you're going to get something very, very, very small. So if we go anywhere to the left of charge 1, essentially what we're asking the math to do is to take a really big number, subtract from it a really tiny number, and get 0. And is that going to happen? Does that make any sense? And the answer is no. If we actually try to carry out the math for this, what is going to happen is that we're going to get an imaginary solution. And that's not going to work for us. We need a real solution. So just by stepping through the concepts in the math there, we've saved ourselves quite a bit of time, because to set this up and to go through a solution just to find out that our solution is going to be imaginary can be a bit frustrating, because we haven't gotten anywhere. We got an answer that does not exist. But just using those concepts with the math and with the physics shows us that not only are we going to be able to skip everything in between the charges in terms of searching for a solution, but nothing to the left of charge 1 is going to work either. So now let's consider everything to the right of charge 2. And we'll go back to this ratio combination here. We'll see what happens. Now that we're to the right of charge 2, so we're not going to consider anything over in those areas. But now that we're over to the right of charge 2, I can say that the distance between Q2 and where I want to measure things, that's R2. And the distance between Q1 and where I'm trying to measure, that's R1. And so now we've seen the situation flip. R1 has now become the larger of the separation distances, and R2 has become the smaller. But Q1 is still the larger magnitude of charge, Q2 is still the smaller magnitude of charge, and so now we have a large charge divided by a large separation distance, and a small charge divided by a small separation distance. And so now these ratio combinations are going to make for a much more realistic approach to finding a solution to this problem. And so this is where we're going to focus our attention. I'm expecting our solution to be somewhere to the right of charge 2. And we are going to now begin setting up the math to solve for this system. And I'm going to start right back here with our ratio. Now that we know that this particular location somewhere to the right of Q2 is going to work, what I'm going to do is I need some way of relating R1 and R2, because physically they are separated by a distance of 4 centimeters. Q1 is over here at -1 centimeter, Q2 is at +3. And so what I'm going to do is I'm going to say that R2, which is the distance from Q2 to the point out in space where I'm trying to measure everything. Again, I don't know where this point is. And so don't deceive yourself in thinking that that's 5. This is just some random point on the number line. But let's call that X. The distance from charge 2 out to where we're trying to measure things, that's X. And if that is X, then R1 will have to be X plus the additional 4 centimeters that exists between charge 1 and charge 2. And these values are then going to be inserted into this expression. All right, Q1 over R1. R1 is now X plus 4 squared. minus Q2 over R2, which is now just x squared. All that has to equal 0. I'm going to move the Q2 term over to the other side of the equality. And the reason I want to do that is we have a little bit of exchanging to do here. We're trying to solve for the value of x, and that's going to be difficult if x is down in the denominator. So I'm going to do a cross multiplication to move those denominators up, and that means we'll have q1 x squared equals q2 x plus 4 squared. We need to expand upon that binomial on the right hand side. So go ahead and FOIL the x plus 4, and when we do that we should get x squared plus 8x plus 16. Then what I'm going to do is I will subtract the q1 term over to the other side. So if we subtract q1 x squared from each side, we're back to having everything equal to a 0. But the reason I want to do that is so that I can combine the x squared terms. I have a q2 minus a q1 all times the x squared. But then I also have to have q2 multiplied against everything else that was inside that parenthesis set. So q2 8x plus q2 16. The reason for this is because when we go to solve for x, x is going to be a quadratic solution. And for a quadratic solution, the solution to that is negative b plus or minus b squared minus 4ac all over 2a. So this should have been seared into your brain back in high school. But now we are set up to find the coefficients a, b, and c for this quadratic equation here. And the first step is to set the equation equal to 0, which we've done. And now we have to identify our coefficients. The a coefficient is all the stuff attached to your second order term. The b coefficient is everything attached to your first order term. And then your c coefficient is your 0th order term. And it's at this point where I'm going to introduce the values of the charge, because I will need those to solve our quadratic. So back up here, we had negative 50 and 20. But keep in mind, everything in here is in absolute value form. So Q2 minus Q1, Q2 was 20, Q1 was magnitude 50, so we're getting a negative 30 for A. Don't forget your units there. So this was microcoulombs, and so everything needs to be 10 to the minus 6. B is the magnitude of Q2, which is again 20 times 8. so that makes for 160. Again, the unit of Q2 is microcoulombs, so we have 10 to the minus 6. And then C is 16 times the magnitude of Q2, so that's just twice as much. Again, 10 to the minus 6. And those values have to go into our quadratic equation. So here we go. One step at a time. We have negative b plus or minus b squared, 160 10 to the minus 6 squared, minus 4 times a, 30 10 to the minus 6 with a negative, times c, 320 10 to the minus 6. And again, we can't have any imaginary solutions, but that doesn't look like it's going to be a problem because everything underneath that root is going to come out to be a positive. Then we need to divide by 2 times the value of a. Okay, there we have it. So now the trickiest part here is just being very careful with our algebra and evaluating everything as we go along. Out front here, we're going to have our negative 160 10 to the minus 6, and I've already calculated everything on the inside for our square root, and what I get is that all evaluates down to a 253 10 to the minus 6, and then in the denominator we just have twice the value of a, which would be negative 60 10 to the minus 6. And so now, since everything in line has a 10 to the minus 6 attached to it, we can factor those out. And we're left with a much more manageable set of numbers. And like any quadratic solution, you're going to get two answers. The question is, which of the two answers is a valid answer for our system? Well, remember that you're looking for something to the right of charge 2. So we need to get some number that is at least bigger than 3 centimeters. So that's what we're looking for. If we get anything smaller than that, then it's not a real solution for the system. Well, so I need this to come out to be positive. And the only way that that's going to happen is if I choose what I call the negative path in the solution. So I'm going to incorporate the negative of the second term. Otherwise, if I add the positive term, the top becomes positive. Then I divide by the negative in the denominator, and I get a negative answer. And I can't have a negative x value. But by combining the two negatives in the numerator, I get a negative numerator. Then I divide by the negative denominator, and that turns it into a positive solution. And so I get a value of x that is equal to 6.88 centimeters. Now, keep in mind, where has x been measured from? And we said that the length of R2 was equal to x. So starting right there at Q2 and measuring out, that is the distance of x. I have a solution of 6.88, but this is 6.88 centimeters away from charge 2. I would have to add the additional 3 centimeters to get the value as measured from the origin of the system. So in terms of the origin, x would equal 9.88 centimeters. So that is where we are going to find an electric field equal to 0 in our system. Okay, well, I realize that that's a pretty algebra-intense example problem, but that's kind of the point. As far as all of the calculus goes, I very rarely see students really struggling with the calculus, but when it comes back to the algebra, trust me, everybody still struggles with algebra from time to time, including myself. In fact, I went through and I did this problem with pen and paper before I came here to record this, because I wanted to make sure that I had all of my algebra correct. So if you do run into situations where you just have an answer that doesn't make sense, that happens, and it is a responsible thing for any engineering or science student to criticize your own work and just make sure that what you have in front of you is an answer that makes sense. And if it doesn't, you need to go back and review your work. All right, well, I promised you a second example problem, so let's give that one a shot. Now, for this one, what we're going to do is we're going to go from a system with 2 point charges to a system with 2 ring charges. So I have 2 charges that are going to be spread out over the 2 rings in this system, and we'll say that the radius of ring 1 is equal to the radius of ring 2. And we'll say that ring 1 is currently centered at the 2 centimeter mark. Ring 2 is currently centered at the 7 centimeter mark. And halfway in between, actually let's move Q2 over one more so that we're not dealing with any half centimeter values. We'll bring Q2 out to 8 centimeters. Come on. Okay, so now we have our 2 rings, equal radius, even though it doesn't quite look like it in the picture. But that's the drawback of trying to draw anything. But they are separated by 6 centimeters. And between the 2, at the, let's see, you've got to count over 1, 2, 3, 4, 5, 6. At the 6 centimeter mark, we have, let's see here, I want to reduce the screen here just for a moment. Oops, that's not what I wanted to do either. I was looking to see if there was a way I could pause the video, but oh, that's okay. What I want to do right now is I want to go and get the equation for the ring of charge, and I know we have that in a previous lecture, but in the meantime, what we can do is we can go to Wiley Plus and log in and go to the Read Study Practice section. So obviously that's not what you're going to see, that's the instructor's view, but since I don't have all of these equations committed to memory here, we need the electric field of a charged ring. I think that should be paired up with the... Oh, here we go. There's the ring. And we'll head on down to where they have their solution. A little bit further. A little bit further. Okay, there we go. So I'm going to jot that down real quick because we will need that. And just in case that does look a little strange, remember that our author has begun writing K as 1 over 4 pi epsilon naught. So we're going to need that. And we'll expand back to full screen there. So at that 6 centimeter point, if the ratio of the two fields at that point, so in other words, if the electric field being produced by charge 2 is twice as strong as the electric field that is being produced by charge 1, what is the charge ratio of the two rings? All right. Now I've purposely chosen not to have the point where we're measuring things be directly in between the two, because then the charges would just have to be the same. So I've offset it a little bit. So when we look at that 6 centimeter mark, ring 2 is 2 centimeters away and ring 1 is 4 centimeters away. And since we know what the ratio of these two are going to be, we can now start putting together some math. So we know this ratio is equal to 2. So what we can do at this point is we can take our equation for the magnitude of an electric field, which is QZ over 4 pi epsilon Z squared R squared to the 3/2 power. Excuse me. And let's remind ourselves of what Z is. Z is the measure from the center of the circle out to where we're trying to measure. And so ring 1 has a Z value that is equal to the 4 centimeters, and ring 2 has a Z value that's equal to the 2 centimeters. The R value in these expressions right here, that is the radius of the ring itself. And we already said R1 and R2 are going to have the same radius. So we'll just call that R from now on, instead of trying to differentiate between the two. Okay, so this equation is what we're going to use in place of the two fields. We just have to plug in the appropriate values. So I'll start with E2, since that's over there on the right. E2 is going to be based off of the charge, which is Q2. Z2 over 4 pi epsilon naught. We have Z2 squared plus R squared 3/2. So there's E2. That has to equal 2 times the value of E1. And E1 is going to be Q1 times Z1 all over 4 pi epsilon naught Z1 squared R squared 3/2 power. Now that we have that, there's a bit of cleanup that can be done. Just like in the previous example, we can see that the K value is common to each set, and so we can eliminate that right now. We don't need the 4 pi epsilons in here. And now we said, see, what was it we were asked for again? We wanted to know what was the ratio of the charges. So, and I didn't specify if I wanted Q1 over Q2 or Q2 over Q1, but whatever we get here, if we need to flip it over, we can do that later. So we want Q1 over Q2. So the first thing I'll do is I'll divide each side by a Q2 so I can at least get the combination that I want. And then I'll work at moving everything else over. So I have, let's see, I have Z2 over Z2 squared, R squared 3/2 power. And then I need to start moving everything from the right side over. I'm going to divide by Z1. So I'm going to divide by Z1. I'll bring that Z2 over here. I will need to multiply by the Z1 squared R squared 3/2 power, so that's going to come up to the numerator. Z1 squared R squared 3/2 power, and then I'll have to divide over by the 2. And there we have it. There is the ratio of the charges that will make this into a true statement. Now, I have given the values of Z1 and Z2, so the only thing left is that I would need to provide a value for R. And let's see here, R, let's let R be 5 centimeters. So now that we have numbers for everything, we can plug in everything that we have. We have Z2 in the numerator is 2 centimeters 0.02 over Z1, 4 centimeters, 0.04 times 0.04 squared plus 0.05 squared, 3/2 over 0.02 squared plus 0.05 squared, 3/2. Calculator time. And if you want to, you can actually combine those 3/2 power ratios because if you remember the root of a ratio is equal to the ratio of the roots and vice versa. So that at the very least could cut down on the number of steps that you have to take. Right here I've got a 0.02 and a 0.04. That's just going to reduce to a half. And in the numerator here, I'm going to end up with 0.04 squared plus 0.05 squared, which is 0.0041. And then in the bottom we have 0.02 squared plus our 0.05 squared, which is 0.0029. And so we can combine those. The 1/2 and the 1/2 will combine to a 1/4. So again, it's all about being careful with your algebra. Try not to combine too many steps in your calculator all at once. That's a recipe for disaster. Everything that I'm getting inside of that first set of parentheses, 1.414, we need to take that to the 3/2 power, and then we can multiply by our 1/4, and so I'm getting 0.42 as the ratio of the two charges. And what do you know? Looks like 42 is the answer to everything. And no, I did not plan for that to happen. I just made up these numbers as I went. But no, 42 is not always the answer to everything. Just in this case. So whatever the value of charge 1 is, it's going to equal 42% of whatever charge 2 is. And so what this means is that really I could put any charge that I want on charge 1 or charge 2. If I said that charge 2 was equal to 100 microcoulombs, then charge 2 would have to be 42 microcoulombs, and then I could put everything into this expression and it would lead back to this relationship, that the magnitude of field 2 would be twice as strong as the magnitude that field 1 was producing at that point. Now, that is not to say that we have solved for the net field at that point. That is a completely different problem. If I want to know what the net field is at that point, then we would need to find numerically what are the values of field 1 and field 2 at that 6 centimeter point. And for that, we would need to know the Z values, the R values, and the Q values. So now that we've introduced that, now that I've specified an actual combination of charges, if you wanted to find the net field at that location, you could do that. I've given both of these rings positive charges, and so that means that whatever field that ring 1 is producing is going to be pointing away from ring 1, and likewise ring 2 is going to have a field that's pointing away from ring 2. Because these fields are opposing, the combination of these fields is actually going to end up as a difference, because now we can see that since our two fields are pointing in opposite directions, if we wanted to assign a positive direction to our system, which I guess we already have given the numbers here, in that case we could set up the system, add them up, and see what we get, and don't expect it to be 0. There will be some homework problems where they might set it up to be 0, but don't expect that. It could very well be something else. And given that ring 2 has a much larger charge, and that ring 2 is much closer to the point in question, my gut instinct is that since the magnitude of charge 2 is so much larger than charge 1, in fact there should be a 2-to-1 ratio there. If E2 has a magnitude that's equal to twice of E1, then we should get a magnitude at that location that is equal to the magnitude of E1. Kind of interesting how the algebra kind of collapses down to that. It just happens to have a final direction pointing to the left. Alright, so those are the two example problems that I wanted to show for this electric field material. Obviously there are a lot of other field expressions that you could go with. Remember, there's the line of charge, the disk, there's the dipole. So it's going to be very important that as you go through your homework assignments and any quizzes or tests that you're grabbing the right equation for the situation at hand. I've seen plenty of students on a test. They're working with a disk, and they're trying to find the field up here, some distance z, and they use the ring expression. Well, a disk is not a ring. Arguably it's a very, very, very thick ring, but that's why we went through the derivation to show the difference between the two. You need to make sure that you're using the right equation for the right situation. Otherwise, there's nothing that's going to go right in that problem. All right, when we come back, we start chapter 23. So we'll see you then.